Alright, hey everybody, this is the first actual lecture that has physics content in it, so it's not just an overview of the course, so it's an exciting thing. We're actually going to get into a little bit of electricity, electric forces today. So the first thing I want to do is, this is one of my favorite videos. It's a little bit old-timey, but it's a nice discussion of electric forces. And so to do that, what I have to do is I have to mute my microphone so that the only thing you hear is the pre-recorded thing. So just give me a second here and I'll go ahead and do that.
Electrical forces are of enormous importance in nature. On the atomic scale, they far outweigh any gravitational forces. Electric forces hold atoms together and make steel wires strong. They also hold atoms apart and make, for example, water difficult to compress. I have here a tube which I'm filling quite full of water, and a piston which fits and will fall, just fits. It will fall slowly like that. It just fits. Now put this down on a squashy rubber sponge, let go, and give it a sharp crack with a mallet. Water is practically incompressible. In fact, electric forces hold the parts of atoms together, electrons and nuclei. If you want to understand atomic physics and really make much of the models of atomic structure that we use, you've got to know the law of force between electric charges. We are going to investigate a universal law of force between electric charges. At small distances, electric forces compete well with gravity. Turn on my charging arrangement, please. Give a charge to the balloon. Collect a like charge on my balloon. They repel. At closer approach, more. Bigger force. Now, farther away, less force. Still farther, very little force. Now give an opposite charge, and I get attraction. What is the exact relationship between force and distance? You probably know already. Coulomb's law says force varies inversely as the square of the distance between the charges. That means that at twice the distance apart, the forces are a quarter as big, and at 10 times the distance, they drop to 100th.
Okay, let me unmute myself there. So I really love this video. One of the things I love about the video is, the fact that they're like breaking these mallets and, without any safety gloves on and things like that. So I'll talk about that in a second, what exactly was happening in that part of the video. One of the first things that the video talks about is how electric forces make steel wires strong. Well, what does that mean? Well, when you have a steel wire, you have atoms that have some sort of bond between each other. I'm not a chemist, so I'm going to screw this up. But broadly speaking, when you have molecular or any kind of bond, you have an electron that is sort of shared between two nuclei. And so why are steel wires strong? Well, the electron here is attracted to this positive nucleus here, or this positive ion, let's say. And then this electron is also attracted to this positive ion, right? So there's attraction here and attraction here. And so there's a lot of attraction going on. And so it's going to be a very strong thing. And so if you try to pull it apart, well, the fact that these two things are attracted to each other is going to resist that. And so you're going to have to pull very strong until you can overcome the electrical forces that are holding these things together, is sort of the point. The other thing that the video talked about is how electric forces makes water practically incompressible. What's meant by that is that, I mean, this is not exactly a water molecule, but water has, you can think of this is a very vague sort of picture here, but there's a positive nucleus, right, and then there's electrons around it. I know this is not like the Mickey Mouse or water thing, but it's the same basic principle. So the electrons are out here, the nucleus is in here. Well, if you put these two atoms together, the electrons are going to be right close to each other. Like charges repel, and so if you try to smush this atom into that other atom, well, the electrons are going to repel, it's going to resist that. And so if you try to push hard on it, it's not going to get them any closer together. And in fact, the only thing you're going to do by sort of pushing down on this thing is transferring that force to the bottom of the container. And if you put enough force, it's just going to make the bottom of that container crack, which is what they showed in the video. So again, the incompressibility of water, this phenomena, relates ultimately back to the fact that these things are repelling. And this is the principle behind hydraulics and all this stuff. We even talked about fluid mechanics in Physics 1250, but we never really said what was going on and why it was happening. We just sort of said, I would just say things like, oh, the atoms are all smushed together, they can't smush anymore. Well, why can't they smush anymore? It's because they have electrons that are repelling each other. Okay? So what is a conductor? What is an insulator? A conductor is some sort of material in which the electrons are free to move. So if you look at these little minus signs, the electrons are negatively charged. When we bring in positively charged things, the electrons can move all the way from this side up as close as they can to get to this positively charged things. Not all the electrons, but just enough electrons to sort of to respond to that electrical charge. So there's still electrons over here, but the point is that there's free electrons in here that can move around in response to whatever is going on up here. That's a conductor. An insulator, which we'll talk about, the electrons can't move nearly as far. I'm going to talk about that in the next slide. Now, you might wonder, like, well, what about the ions here? Why don't the ions move when you have like a negative rod up here? Well, and so they're heavier, so they're not going to move as much. And so typically in this course, the electrons are going to be moving around, the ions not as much. The only situations I can think of when ions are moving around are like certain types of batteries. We have sort of ions sleuzing from one side of the battery to some other thing. If you try to run electrical current through salt water, I believe that does cause the salt ions, the sodium ions, chlorine ions to sort of move. But in general, the ions are not going to be doing very much. Especially in like a copper and aluminum cable, those ions are going to be basically stationary. Interestingly, plasmas are also conductors. So it's not just things like aluminum and copper that are conductors. When there are lightning strikes, and last week there was a gigantic lightning storm in California that was interesting. When there's a lightning strike, what happens is that the electric forces are so strong that the neutral atoms in the air lose an electron, and so now you have a positive charged ion, you have a negative charged electron. That electron can move around freely. You've got a conductor. So plasmas are all conductors. And that's ultimately why you get sparks, which we'll talk about a little bit later. So an insulator, as I said, the electrons can't move as much. It's not that the electrons can't move at all. If you look closely at this diagram, the electrons can move from sort of this side of the ion to the other side of the ion, or this side of the atom to the other side of the atom. So they're not immovable, but then again, this electron is not moving all the way over here. This electron down here is not moving all the way up here. They're kind of stuck to whatever atom they kind of start with. And so that's what insulators do. Now, I think I just said all this. The electrons have a charge of negative 1.6 times 10 to the negative 19 coulombs. I'll talk about Coulomb units in just a minute. Protons have the opposite charge, and the two are exactly the same, so that if you have a proton and electron together in a hydrogen atom, that atom is neutral as neutral can be. So we call this the fundamental unit of charge. Now, there are things in the universe that have less charge in this. So quarks, for example, have 2/3 of this or 1/3 of this, but no one's been able to find 1/6 of this or 1/10 of this. Despite the fact that people are looking, right? If you could find a particle that had some other charge in this, that would be Nobel Prize territory right away. But people have looked and looked and looked and looked and looked, and they've never seen anything less than, say, 1/3 of this elemental unit of charge. Coulomb was a French guy, and he was able to prove for the first time what you saw in the video, that the force goes as the square of the distance. So this is his law. So this is what I call the K constant. So it's about 9 times 10 to the 9 newtons per meter square, Newton meter squared, or coulombs. Here's a question. So you have two charges. So you have one Coulomb charge and another Coulomb charge, and they're a meter away. So maybe that would be like this far apart. If that was true, is the force between those two things going to be overall big or overall small? Again, if this is a Coulomb and this is a Coulomb, and let's say they're both positive or something. Well, if we think about this equation and think about this this constant, if this is 1 and this is 1 and this is 1, and it's 1 squared is 1, right? Then the force would be, exactly this constant, right? Which is pretty close to 9 times 10 to the 9. Is 9 times 10 to the 9 pretty big? It's almost 10 billion. Like, that's a lot of force. So it's gigantic. So the Coulomb force is huge. Why is this not, some sort of space weapon that we're using? Well, it's very hard to accumulate 1 Coulomb of charge. So in this course, there'll be a lot of, nanocoulombs, maybe a microcoulomb. If we're feeling ambitious, it might be a millicoulomb, 10 to the minus 3 coulombs. So in general, we're not going to have like a pure, like a 1 Coulomb. That would just be gigantic. What's interesting about this is that it's the same as the law of gravity. Gravity is also 1 over r squared force. Has a different constant, and it has the masses up here instead of the charges. But this is somewhat the inspiration for this, for the idea that this picture of the atom with the ellipses on it that you might have seen. We're going to talk about that later in the course. So there's some connections there, interesting connections there. So again, we'll talk about this later in the course. Right. A key difference is that gravity sucks people, right? Sucks. But this can also attract. Another thing to say about electric forces is that they're vectors, and so there's a nice active figure here from the book. I don't know that this figure probably won't work on your devices because it's made in Flash. I think they have a workaround for it, but the point is that if you have a positive charge next to a negative charge, let's say, the force is a vector. It has a magnitude, there's a strength of it, but there's also a direction that it's pointing. Okay? Same thing with, two positive charges together, there's some force that's pointing away from the thing, and depending on where it is, it points in a different direction. If there's multiple different charges, right, then there's multiple different forces, and you just sort of add those forces together. Later we'll have a worksheet. I know this probably seems like some pretty abstract math stuff, but later we'll have a worksheet where there's going to be a string holding an object, it's going to be charged, it's going to be gravity, and so you can treat the weight, the gravity, the string tension, and then also the electrostatic force sort of on the same level. Each one of those things is potentially affecting the position of that object. All right, now something I want to talk about, which I think is pretty fascinating, is that if you look very closely at that video that I showed you earlier, the black and white video, And you notice right after he charges up the balloon, so the balloon is positively charged, and then he takes it over to the balloon that's hanging from the ceiling. That the balloon that's hanging from the ceiling, which is not charged yet, seems to drift forward. So let me show you that real quick.
Electric forces compete well with gravity. Turn on my charging arrangement, please. Give a charge to the balloon.
So did you see that? The way that the balloon sort of like moves towards the balloon hanging from the ceiling, which is not charged yet, actually sort of drifts towards this balloon, which is charged, right? Because he touches this balloon to the positive end here. So this balloon is positively charged. This balloon is neutral. So positive and neutral should not ultimately produce a force, right? So Coulomb's law, Q1 and Q2, if Q2 is 0, then there's not going to be any force. So, but clearly this thing is sort of is moving. So we're going to unpack that in sort of the next few slides. Hopefully you saw what I saw, and you can feel free to play the video back again if you want to see it. The first observation about this is that a similar thing happens when, I don't know if you've ever combed your hair and then put it next to a faucet. So for example, here's a video of it. So they comb the hair. You see how the water gets deflected there? So this is a situation where the comb is charged up because we put it through our hair, and so presumably the comb, maybe lost some electrons to your hair, so the comb is a little bit charged up. Or maybe it gained electrons, I'm not totally sure. It's not pure magic, it's pure physics, my friend. The point that the connection between these two things is that this water coming out of the faucet is not charged. So it's not as if the water is negatively charged and is attracted to this thing. If you got some sort of electric field probe, you would notice that the water is definitely not charged at all. So what's happening here? How can neutral water coming out of a faucet attract to a positive thing? How can a neutral balloon be attracted to a positive thing? It could be a negative thing, by the way. This interactive, which I think is very good, it can kind of help to explain that. So let's go ahead and open this thing up. You guys can feel free to play around with it as well. There we go. I didn't make this, but I have mad respect for the folks that did. So we've got an aluminum can here, and I can show the charges. So there's a bunch of, you see the electrons there, they're sort of on top of the positive charges, the positive ions there. And what I can do is I can introduce a green rod. Sorry, I can introduce a glass rod that is positively charged. And you notice that right away this aluminum can started moving over to that point. Okay? And so, all right, well, I can move it over here. It's fine, all right. So the electron, remember, in a conductor, electrons are free to move. And so what happened was that the electrons that were sort of all the way over here moved closer to this thing, right? Because if they can move, and if they sense that there's a positive charge there, right, they're attracted to positive charges, so they're going to move towards the positive charge. Why does that result in the can moving? Why doesn't the can just sit there? Well, the thing is that if these electrons are closer to this thing, and these are further away, well, these electrons, the force goes as 1 over r squared. So the force between these electrons and this thing, because the distance is smaller, is going to be more than the force, like the attractive force of these electrons to this positive charge, right? So unlike charges attract, opposites attract, this force is going to be more than the repulsion of these positive charges. These positive charges are repulsed by this thing. They want to move in the opposite direction, not towards it. But because the electrons can move, the force on the electrons is more than, the attractive force on the electron is more than the repulsive force on the positive things. So at the end of the day, this thing sort of follows this thing around. Now, what happens if I have a negatively charged object? It's like, does the opposite happen with a negatively charged object? It's a good question. By the way, this thing is fun. You can kind of like kick the can. I find this to be very entertaining. All right, I'm going to turn off the glass rod. Self-restraint here. All right. Now I'm going to bring in a rubber rod, which is going to be negatively charged. So I guess when you rub a glass rod, it becomes positively charged. The rubber rod, if you rub the rubber rod, it tends to accumulate negative charges. Is it attracting or repelling? Right? It's a different charge, so you might have thought that it would repel, right? Because in the video, it was a positively charged balloon attracting a neutral thing. I mean, clearly this can is neutral, right? It's the same number of electrons as there is positive ions. But what's happening here is that these positive charges are attracted to these negative charges, right? They're attracted. These electrons are repelled from the negative charges. And because the electrons can move, they move further away. And so the force between the attractive force here, because the force goes as 1 over r squared, is more than the repulsive force of all these electrons that are all the way over here. So because the electrons have some ability to move, this ultimately causes the can to be able to kind of move in attraction. In spite of the fact that the can is overall neutral, it moves in response to these external electric charges, so that makes sense. Now, balloon obviously is not a conductor. It's not an aluminum can. But there's some capability for the electrons to move. Even if the electrons are moving from one side of the atom to the other, that is enough to get it to move just a little bit. So again, because the electrons move, you end up with these sort of attractive situations. But what you can't do, what there is no way to do, is there's nothing that you can do to get a neutral object to repel. So if you bring in a positive charge, it attracts. If you bring in a negative charge, it attracts. People have looked for weird situations to get neutral objects to repel from other things. Haven't found anything. So this is what we've got, if that makes sense. All right, I'm going to close that. Close that page so it doesn't eat up my processor. All right, I think I just said all these things. All right, now here's something new. So let's say that you have, I forget if you have whether this video starts with a positively charged object. So let's say you have a positively charged object and you want to have instead a negatively charged object. Or maybe you have a negatively charged object and you're just like, oh man, I wish I really had a positively charged object. I want to, I want the other thing that I don't have. Well, there's an effect called charging by induction that allows you to do something like that. So I'm going to mute my mic again so that you don't hear this terrible echo and play the.
A conducting material contains within it electric charge that is free to move. The gray sphere shown here is a conductor that initially has no net charge. When the blue ball representing a negative charge is brought near, some of the positive charge in the sphere is attracted and some of the negative charge is repelled. The net rearrangement of charge in the conductor is indicated by the coloring of the sphere surface. When a conducting path to electrical ground is connected to the sphere on the side opposite the external negative charge, the negative charge on the sphere, repelled by the external charge, can flow off of the conductor. Removing the conducting path leaves the sphere with a net positive charge. When the negative charge is removed, the sphere retains this net charge. This process is referred to as charging by induction.
So again, they started with a negative charge. So all they had was a negative charge, and we really wanted this thing to be positive charge, right? But by bringing it close and then touching this thing with a conductor there and allowing the negative charges in this thing to sort of leave, what's left behind is positive charge. So it's kind of an interesting way of charging things up. Now, the group work for today actually relates somewhat to the experiment. So technically the day is a lecture day instead of a lab day. But part of the lab, the first lab, involves this kind of worksheet thing that's related to experiment I'm going to tell you about just now. So today is a mix of lecture and lab, you could say. I'm also saying that because, there's a lot of questions like, how are we doing a lab in this course? Well, the next slide is a video of part of the lab, not the whole lab, but part of the lab for this case. So everything from here on out is what you would already be doing in the lab course. So this contraption is going to become highly charged. I forget if it's becoming highly positively charged or highly negatively charged. And then these two aluminum cans are connected to it, so that as it becomes highly positively charged, let's say, I don't know if it's positive or negative, but one of the two, you know, this thing gets charged up and this thing gets charged up, but they're the same charge, and so these cans kind of repel each other. And the more charge that they have, the more that they actually repel. And the question is, the worksheet is to say, based on how far apart that they are spread, can you tell me what the charge is on those objects, like in coulombs? There's also a video. So this is what you get for watching the full video. This was another video that I found that I thought was interesting, and so this thing is going to charge up, and so this thing charges up, and it gives some of that charge. I don't know if it's positive or negative, but you know, let's say this is positive, that becomes positive, that becomes positive. Now they're all repelling each other, and then they're going to move this thing away, and you'll notice these two pieces of metal are still repelling each other. Like, even though this thing has moved away now, you see how they're sort of still kind of repelling each other because they have a good bit of charge on them and they're repelling. Yeah, kind of like that. So not as like ideal is sort of what we're trying to do for this worksheet, where you have, you know, which is, you know, two things that are suspended and they're repelling each other. But you can kind of see the kind of effect that you can do here. So I think this thing is probably more effective than whatever we were using in the video from Columbus here. So that's, in any case, that's the setup. And there's each one of these things is 1 kilogram. And the question is sort of, just by observing what this angle is, can we figure out what is the charge on each one of those things? So that's the worksheet to today that you can do with your groups. The hint that I will give, and I gotta admit, this is kind of a tough worksheet to start on. So if you've had the whole summer since you did Physics 1250, this worksheet is going to be a little bit of you might need a little extra coffee for it. But this is a hint. The hint is that each one of these balls is on a string, and so there's some string tension pointing up this way, right? There's also the weight pulling down, and then each one of these balls is being electrostatically repelled away from the other one. So basically each ball has 3 forces applied to it. And another important thing is that this is a static configuration. So the video from Columbus didn't do a great job of sort of like spreading these things out and sort of like waiting for them to kind of stop. They would sort of like wiggle around like this. So let's just say that they're sort of stopped like this. They're repelling each other. They're being pulled to the ground, but then the string is holding it up as well. So let's just say that this has all sort of reached a kind of equilibrium, and we're in a position to measure this angle and try to figure out what the charges are. So the question again is, what is the charge on these balls in this situation if the angle is 5 degrees and if the 2 balls are 1 kilogram? So that's the challenge for today. And when you're done with that, you can go ahead and submit that to Carmen for us to look at. So huddle up with your group. We'll click the Zoom breakout, and we'll go from there. So we'll all help each other to figure this out.